Alright everybody, I kind of wanted to talk a little bit of why the centroid and why the moment of inertia, and I kind of wanted to try and tie it in. So kind of a quick little review. And we talked about this when we did our internal loads of a beam, and we have our bending moment. And if we did this, we'd have some kind of neutral axis right here. That'd be our neutral axis, because on the top here we can see that the beam is in tension. Is in compression. Sorry. Getting ahead of myself there. Compression. And the bottom is actually in tension. And this is when we have a positive bending moment. Remember, our orientation is our positive bending moment. So those are positive. And then we have our negative bending moment. So we have something that's going to look like this and like this. And again, we would have our neutral axis through the beam. And this would be a negative bending moment. And now we can see that this side is in compression and this side is in tension. So if you kind of looked at this and we kind of cut the beam, so we're kind of looking at the beam on the side view, and we kind of did this. Let me rewrite that. I kind of did something like this, looking at the side of the beam, and our neutral axis. So our neutral axis is, here's our neutral axis, where it's shown here. That's our neutral axis. We'll call that X. And this would be our Y. We would have something that looks like this. So we said that the top is in compression, so this is actually going to be going in, and in tension it's actually going to be going out like this. Just a kind of a diagram there. And then down here it would look something like, again, cutting the side, and we'd have something that looks like this and like this, where again our neutral axis is cutting right through there. And on the tension side it's going to be going, distributed load is going to be kind of going out, and on the compression side it's going to be shown going in. So what we mean by that is if we're looking at the side, if we cut it and we looked at the beam, and let's say it's some kind of U-shaped beam, some kind of U-shaped beam like this, and we must find the centroid of the beam. That would be my Y. Now this would actually be my Z-axis since I rotate it around. And so when we're looking at this, and when you get into mechanics, you're going to look at the flexure formula. And when you're looking at the flexure formula, we get that sigma x is equal to a negative my over pi. Sigma x is our bending stress. And m is actually our bending moment, which we could find using a shear and moment diagram, or cutting the beam at a certain place and computing that moment. And y is the y coordinate, and that's the neutral, at the neutral axis. And I, if we can call this IZ. IZ is the moment of inertia, about the Z-axis. So I kind of wanted to touch on that just a little bit, just to kind of show why we're computing this. So you had to compute the centroid, and then so that's your neutral axis, and then you have your bending moment, and now we're computing our moment of inertia. So kind of want to throw this all in before I went into the next example, which is, you see, it's the same shape that we did before and we found our centroid. But the first one I'm going to do is I'm going to compute the moment of inertia about the axis as they're shown there. So we're going about the y-axis and the y-axis and the x-axis. So as discussed before in other videos, our two formulas are the moment of inertia about the x-axis is our ix prime plus ADY squared, and this is the parallel axis theorem. And in this case, since they're rectangular shapes, our Ix prime is equal to 1/12 the base times height cubed. Now these shapes, any types of shapes, circles, half circles, the triangular shapes, they all have their own formula, and you can find these in the back of your book. So take a look at the back of book, because you might be able to use these for your final exam. So let's set up a table. You know me and tables, I like tables, easy for me to use. So I'm going to compute, I'm going to make, let's just do two tables. That's one ugly line. Let's try that again. Alright, so if I'm computing my moment of inertia about the x-axis, I'm going to have my segment, I'm going to have my area, this would be in inches squared, I'm going to have my distance, and that's going to be in inches, and then my Ix prime comes from this formula, and then I'm just going to go ahead and add up my ADY squareds, and then I have my Ix prime, my ADY squared. I can add those to get my moment of inertia about the x-axis. So this here are those two there. So again, if I break this up like I did before, where this was 1, this is 2, and this is 3, I'm gonna have 1, 2, and 3. And since we've already done this problem, we know that the areas were 2, 10, and 7 inches squared. Now dy. Now what's dy? Well, dy in this case is going to be the distance in the y direction for segment number 1. So it's going to be to the center. So there you go. It's the centroid of that segment. We had already computed this. That'd be 1, and then halfways would be 2. So we kind of already solved for that. For this segment 2, again, it's halfway up. And for our segment 3, we go up 1. So this would be 7 inches if you recalled. So that's going to be a total of 4.5 inches. So using the Ix prime, this equation, it's 1/12 base times height. So 1/12 base times height. So our base for number 1, our base, if we're looking at that rectangle, as so, we know our base is going to be 1 inch, and our height is going to be 2 inches. So base was 1 times 2 cubed. And I'm going to do that for the rest of them, so I'll have 1/12. The base here is 10 times 1 cubed. And then the last one is 1, which is my base, times 7 cubed. So putting those into my calculator, I got 0.667 and 0.833, and then the last one I got 28.6. Now just multiplying the area times the distance, but it's squared, throwing those in my calculator, I got 8, 2.5, and then 141.75. So now just adding my Ix prime and my ADY squared, I get 8.667, I get 3.33, and I get 170.35. So by summing all these up, I get 182.3 inches to the fourth. So my moment of inertia about the x-axis is 182.3 inches to the fourth. Now I can do the same thing for my IY. So I'll set up the same table. I'll have my segment. I'll have my area. And something you may want to do is pause the video and see if you can compute the moment of inertia about the y-axis. It's going to be x and IY prime and ADX squared, and this is going to be my IY. So again, 1, 2, 3, my areas stay the same, 2, 10, and 7. Now the the dx would pretty much be the same as your centroid to the x. So moving along from the y-axis, I get 0.5. That's the x to the center of segment 1. Now I'm going to get 5 from the y-axis to the center of segment 2. And then I'm going to get 9.5 from my y-axis to this point here. That's halfway of segment 3. So using this formula again and plugging it in, now this is a little different. You could use this formula, IY is equal to 1/12 base cubed times the height. So just remember that when you look at this, the base now, right? The base now would be if you turned it. So it's all about if you rotate it, but your equation is still, which is now the if you rotated the height or the base, just depending on how you're looking at it. So this formula you can use if you're going about the y. So just throwing those in and plugging them in, I get 0.167, 83.3, 0.583. So 83.3. And then again, multiplying area times the dx squared. This here I get 0.5. I get 250. And I get 631.75. So my IY then is 0.667, just adding them all up, 333.3 and 632.3 for a total of my IY, moment of inertia about the y-axis, is 966 inches to the fourth. Now, many times we go about the x-axis, but sometimes what they'll do is they'll come in and say, they'll do something like this, and they'll say, I'm going to take that out. They'll put the centroid in here, and they'll mark the centroid in here, and they'll give you this axis as your x prime, and this axis as your y prime. And you'll have to compute the moment of inertia about the x prime and y prime. And that's the next example. It changes a little bit, and the only thing that changes though are my dx and my dy. Everything else will stay the same. So stay tuned for the next video. Thanks guys.